Okay, so let's start. There are two concepts, electric field and electric field strength, which is also called intensity. So we have two things, electric field and electric field strength. Electric field strength is the measurement of is how strong the field is. So it's a quantitative measurement, and the field is the concept which we need to understand. So when we have a charge, let's say we have any charge particle. The moment a charge particle is born into this universe, it sends the field everywhere. So the field will be created in the entire universe, and theoretically the field will be spread up to infinity. Not definitely, it will follow the inverse square law and will decay as you go away from the charge itself. So field is, you can say, as the region of influence that every charge is capable of. So this is the region of influence in which if any other charge will come, then that charge will experience some force, or you can say it will interact. So Q is, let's call the source charge, and this source charge has created a field around itself, and theoretically it goes up to infinity. Now infinity need not to be very large. It could be as small as a nanometer. It could be as small as, yeah, nanometer is quite small. It could be small as like angstrom range. So it is quite possible that even the angstrom can act as a infinity. And we have quite a good examples to understand this concept. So when you talk about the atom, the nucleus is a charge, and the nucleus creates the field around itself, which is spread up to infinity. But at the same time, the orbiting electron also creates seemingly opposite field, and these two try to nullify each other over a distance, not very close. So as you go away from the center of the nuclei, within the dimension of atom, the field is quite significant and they do interact. We have seen this in the atomic structure, in which the electron interacts with the nuclear force and performs the circular motion. That is how we have the Bohr's model of atom. So the electron is under the influence of field of nuclei, but that field is not long lasting. So as you go away from the nucleus, the field starts diminishing. And even after walking roughly 1 angstrom ahead, the positive of nuclei and the negative of electron, they together starts creating almost close to zero field, a field which is almost negligible and non-measurable. So we say that, okay, the infinity has come for the entire system. If you take the atom as a system, then atom is able to create the electric field, but the range is short-lived. You can say up to few angstrom, it will have the influence, and then as you go away, the together, like the positive of nuclei and the negative of electron, together they cancels out each other effect. In cases when they don't cancel, they behave as a dipole. That is what we call dipole. When the positive charge and negative charge, their field do not cancel exactly, what we call is called dipole. So what you can realize that it is not that the nucleus is not able to create a field. It is able to create a field. It is also not like the field is not going to infinity. It is going up to infinity. But the opposite charge called electron also creates the opposite field. And these two field eventually cancels out each other over a large distance. And the distance is not much. It's just angstrom. So that's why the atom is signifying a confined electric field, a field which is quite, you can say, in a packet. It's confined within the dimension. Now, the region of influence will get over after some distance from the nuclei, and that is how we define the dimension of atom. So of course, no one has seen the dimension. I mean, you cannot measure it physically. So this is not a physical dimension that we talk about. So it's a dimension as per the assumption that the distance from the nuclei up to which the influence is present. We call there is a atom or atomic region, you can say, and beyond that, the atom loses the identity, and then we say that okay, atom is of this size. So of course, as the nuclei size will grow, the positive charge will grow in value, and at the same time, the electrons will also grow in value, and therefore the cancellation will take some more distance. So a large atom will have some somewhat greater area of or region of influence, and so the dimension will increase. So the way we talk about dimension is not the way you understand. Dimension all about the region of influence. Okay. So when we say dimension, we talk about the up to what region of influence the field can exist together. Okay. So that's the meaning of dimension of atom. So every charge is capable of creating its own field. Of course, when you measure it, you won't get the field of individual charge. If you have multiple charges in a space, then you end up measuring the resultant field, not the field of individual. So it is like if you switch on multiple lights in your room, you cannot say distinctly that the light you're receiving is coming from which particular uh, the appliance, which particular bulb or tube light. So what you see in the end result in the room is the net field of, or you can say net light intensity due to all bulbs and tube lights used there, or you can say all light source used there. Okay. So similarly, if we have only one charge, then of course we can say that the field belongs to only one charge. But what if we have multiple charge in a space? We cannot say that it is a field of this or that particular charge. You end up measuring the resultant field. So practically, when we try to measure it, it is always resultant. Theoretically, you can have some definition and you can say this field, this charge is capable of creating this field, or this charge is capable of creating something else. So the idea is simple. When you have a single charge, then the resultant and the individual will be same. If you have collection of charge, the resultant will change drastically. So we need to be careful about this definition, that the measurement always gives a resultant value. Okay. So field is that is the concept called field. Now the force is the consequence of field. What does it mean? It means when we talk about the force of one charge on another charge, we don't talk about the direct interaction of the force. Rather, every charge creates their own field, and the field eventually interacts with whoever comes in its region. Okay. So for example, if it is a source charge, and let's say if you bring some test charge at this location, let's call it this as test charge, then the first charge must have some field at this location. So the source charge has already created a field here, and this field, let's call it E. The field E will locally push or pull this charge. If the charge is positive, it will be pushed along the field, and if the charge is negative, then it will be pulled opposite to the field direction at that location. So the force in sense of physics, the force always refers to the force of field, or field force. So two charges interact not because they apply force on each other, no. Rather, both creates their own field, and the field in your vicinity will exert a local force on you, and the field in the other charge vicinity will create the local force on that charge. Now technically both terms are to be same. That's very interesting. So what we need to understand or realize, the field always refers to the field of charge actually applies force on any other charge. It is not the charge which applies force, either it is the field of the charge through which the two charges interact. And that is the reason For two charged particles to interact, the physical connection is not required because they can interact from any distance. So as long as the field is present, they can interact. Now imagine the very first question we solved in the chapter of in the previous few classes, that if you have two fixed charge, let's say Q and Q, then the point of equilibrium will be at the midpoint, right?
Yes.
Now, no matter which charge you bring, it will be at rest. Why? Because this midpoint is representing a location or a region at which the field of the two charges will cancel out each other. Now, because of this particular reason, because they cancel each other's field, so practically there is no field existing there. That's the whole idea. So at this location, we do not have field at all. The net field is zero. So when the net field is zero, then no matter which charge you bring, because the field is absent, the force is out of question. And that is why the location of, or you can say the position of equilibrium, has nothing to do with the charge which you brought there. Okay. Because the force is eventually applied by the field. And if the field is absent itself, we cannot talk about the force. So who will apply force on a small q charge? Who will apply? The field of two big charges, let's say plus q and plus q.
Yes.
So if I ask you who will apply force on this charge, what we can say?
Q and Q, small q and big Q.
Correct. It is the resultant field due to the small q and the big Q. The net field at the location due to these two remaining charge will locally apply force on the capital Q. So if I just change the name Q1, Q2, and Q, so the force on Q1 will be due to the field of small q and Q. Force on Q2 will be what?
Q1 and Q.
Due to field of Q
Yes.
and Q1. And that is why the force on small q will be due to the field of Q1 and Q2. Okay. Okay. So what is the whole idea of field? Field is simply a region of influence in which if any test charge is brought, then it will experience force of interaction, which could be attraction or repulsion. So let me define the field first. It's a very simple definition. So field is a concept. So what do you say? It is the region around some charge up to which if any other charge is brought, then it will experience the force of interaction. Okay. So what we need to remember about the force? Force is a local phenomena. What does it mean? It means any charge experiences force due to the resultant field present in its vicinity. So this part should be clear to all of you. If you have doubt, you can ask what I'm trying to convey here. So charge do not apply force. The role of charge is to create the field, and the field in turn will apply the force. It is clear?
Yes.
So who applies the force?
Charge.
Field. The job of force is on the field. The field applies the force. So when electron is orbiting around the nucleus, who is applying force on electron?
The field of the.
The field of the nucleus.
Yes.
So it is the field of the nucleus which applies force on electron. Okay. So electron is experiencing force due to the electric field developed by the nucleus. And because the nucleus is stationary, the electric field developed will also be stationary field. And that is why this is the concept of electrostatics. Okay. It is clear?
Yes.
So the field is the cause behind the force. Now, when we talk about the field, let's say if you wish to apply a force on a, or calculate force on a charged particle Q among a large number of charged particles Q1 to Qn. So let's say we have n number of charged particles in space, and their namings are Q1, Q2, Q3, and so on up to Qn. And now we have another charge, small q, on which we would like to find the force. So who will apply force on that charge? The q charge. Who will apply?
All the forces.
The field of
The
all
field of
forces,
all the
all the charges.
charges. Yes.
So now the obvious question is, the field is a kind of measurement of strength. The field strength is nothing but the effect of the force that they can develop. Okay. So even the strength of electric field is determined using the force method only. It is the Coulomb's method that we use to find the strength. So what exactly is strength? So given a charge Q, we know that as you go away from the charge, the strength will decrease or diminish. So if you are at a distance r from the charge Q, and let's say the point is P, then how strong the field will be at point P? So what is the way of knowing this answer? How strong the field is? Okay. So what we do is we bring some test charge at this location. So let's say we bring some test charge, let's call Q. And we calculate the force on this test charge. Because these are two charged particles, we can write the Coulomb's formula K Q1 Q2 by
R square.
R square. Now the electric field strength at the point P we simply define as the force that the charge is experiencing per unit charge. So if you bring Q charge, then this is the force. So what if you bring unit charge? The answer will be FQ by Q. And this turns out to be AQ by. So now this is the definition of strength, which is simply the force per unit charge. Okay. The force per unit charge kept at a position in the field of the source charge is called the electric field strength of the source charge. This field that we have calculated is due to which charge? The source charge. The name is capital Q. It is clear? So that's pretty simple. Now the experimental definition is slightly different. So the definition in a correct form is this. So the electric field strength at a point, if you wish to determine the net field at a point, the problem is the force can be experienced by any other charge. So let's say we have a charge Q, And if we wish to know the strength of this charge at a point P, I need to bring some charge here, right?
Yes.
Now, earlier we had one charge capital Q, but now we have two charge Q. So what will happen practically? Practically, these two charges will alter the field of the location. So if imagine if we have just only one charge capital Q, there must be some field which you don't see, of course. But one thing you can say for sure that the moment this new charge will come, what will happen? The existing field will get distorted, isn't it?
Yes.
So it is like you switch on the two bulbs, then definitely the light intensity will have a different value at different location. Am I right?
Yeah.
So how to make the experiment feasible without distorting the existing field? I do not want to disturb or distort the pre-existing field and still want to measure it. So mathematically, this can be achieved if you write the answer like this. Force on charge Q per charge. In the limiting case, charge tends to 0. Now, what does it mean? Anyway, the Q will cancel out if you divide. But even to perform the experiment, I must bring as small charge as possible. Why? Because I do not want to disturb the pre-existing field. And our intention is to measure the field of capital Q, and the coming of any field will disturb it. So when you try to perform something experimentally, this idea should be in your brain that the charge which we are bringing should be so small that it should not affect the pre-existing field. Do you realize what I'm saying?
Yes.
So it is like if I'm giving you a flower to smell, and you have already used a hell lot of perfume in your body. So the smell of your perfume will interfere with the natural smell of the flower, correct? So what is the best way to find the right smell of the flower? The answer is be neutral. Don't use any perfume. Okay. So of course one should not stink as well. So this is the mathematical definition which is meant for the practical measurement. So if you're doing some experiment and your job is to find the field of the capital Q, then the test charge should be small enough not to disturb the field of the capital Q. So this is how we define. And what you can see clearly, this turns out to be how much? So EP we have got the answer KQ by R square. So how to write in vector form? So for vector form, we need to know the direction, right? So for direction, what is the rule? How to find the direction of electric field? So at any location, if you wish to know the direction, the rule is simple. Imagine, now of course, this is not the real thing. Imagine a unit positive charge kept at that location. Or just imagine a positive charge, not unit, just positive charge. What will be the force, repulsion or attraction in this case?
Repulsion.
So the force on the unit test charge will be like this.
Yes.
Now the force on the directional force on the unit positive test charge is called the direction of electric field at this point. So as a rule, the direction will be same as the r vector. So if I draw the r vector this way, then the field will be parallel to the r vector. If the charge is positive and if it is negative, it will be opposite. So that will be taken care by the sign of the capital Q. So the way of writing is r cap because the directions are same. So in vector notation, if you wish to write, you can write as KQ by r square into r vector upon r. I hope you know the definition of unit vector. We have done this in the beginning.
Yes.
So these are two ways of writing of electric field of a single charge. Now, what you need to realize that the formula that we have derived, the formula that we have derived is only for a single uh, particle or single uh, charge, point like charge. So this answer is only true for the, this formula is only true for what? Only true for point like charge. So is this clear, guys?
Yes, sir.
So now, if what if we have the multiple charges in the system? So for system of discrete charge particles, so for system of discrete charge particles, the principle of superposition will be applicable. So we can apply the and what this says, of course, if we have multiple charges, then the field that will exist in the space will be resultant field or individual field. What will exist in the nature?
Resulting.
Only resultant field. Okay, so the principle of superposition says that don't worry. To find the net field at a point P, imagine one charge at a time and think that how much that charge will contribute. So let's say the first charge contributes kq1 by r1q into r1 vector. Similarly, the second will also contribute something, assuming if that is coming alone, none is there. So the principle of superposition allows you to assume that individual contribution can be added together. Understood what it is saying? That you can imagine one charge at a time and then simply keep on adding their contribution. Of course, the addition is going to be vector addition because the field is a vector, so it will have definite direction. So you can keep on adding like this. So the principle of superposition says that to find the resultant field, take a field of one charge at a time, find its direction, and repeat the process due to all other charges, and then add them in vector form because of course the field is a vector. You cannot add the numerical value. You're supposed to add the direction and value together. That's a vector form actually. So you may rewrite this as summation of AQI upon RI whole cube into. Okay. That's a very simple principle. Now you may have some dilemma or doubts. What is R exactly? So R vector is always vector which begins at the charge and goes towards the point at which you would like to find the field. So what is R vector here? Let me talk about the R vector. This vector is directed towards the point P with respect to ith charge. I hope this part is clear. Any doubt in this? What is Ri meaning?
Yes.
So if we have 10 different charges at 10 different locations, so you will have 10 different R values, right?
Yes.
Now the two cases are very important or very interesting. One, when every charge is on the same line, so what will happen if all charges are on the same line? Then all the R vector will be collinear, isn't it?
Yes.
Imagine if all charges are on the same line. Can we say that all the R vector will be collinear?
Yeah.
And in such case, you are really lucky that the vector addition will turn out to be a simple scalar addition, because we have only two possible directions, right or left. So you can choose one of the direction as positive. Let's take right as positive, and let's take a left as negative, and then add or subtract accordingly to get the net field. Okay. So let's do some simple problem before we go to the advanced problem. So imagine we have a coordinate system like this, and at a comma 0, at 2a comma 0, at 3a comma 0, and so on, we have charge. The first charge is q, but second is minus q, then third is plus q, and so on, alternate plus and minus. So what you can understand clearly here, all charges are lying on the same line, isn't it? Okay.
Yeah.
So if all charges are on the same line, how the R vector will look like for each charge? So O is the point of interest. So what is the question? Find net electric field at O. So destination is given to you guys, where we are supposed to find the field, right?
Yes.
So if you draw the position vector for the first charge, it will be like this. Can you see that?
Yeah.
R1 vector. But the second will be like this. Third, and so on. So luckily all will have the position vector in the same direction. Oh, one caution that you have to be careful. While using the vector notation, always put the charge with sign. Simple rule. What is the rule? While using the vector notation, this particular format of writing, take charge with sign. Once again, while using the vector notation, substitute the value of q with its sign. If it is positive, you must write positive value. If it is negative, you must write negative value. I hope this is clear, guys. Any doubt? Hopefully. Now, do we really need to do all such things? The answer is no, that's not required. So if I number the charge 1, 2, 3, and so on, and if I simply draw the O point, you can see that all the odd charge, odd locations will have field left.
Yes.
So E1, E3, E5, and so on will be left side, or you can say directed towards left. Why? Because if you put a
Positive.
plus, if you put a plus one charge here, or any positive charge, all odd position will repel left, isn't it?
Yeah.
Are you getting my point? Yes or no?
Yes.
So to find the direction of field, what we do? We substitute a plus charge at the location where you would like to find the field, and what to do next? You simply check the direction of force. So every charge at a odd location will be repelling this plus charge. Yes or no? Tell me.
Yes.
What about the odd one? So even one.
Will
All the
attract
even will
even.
attract.
Yeah.
So the idea is simple. If O is the place, and if we know that we have to find the net field, so the nearest will be having the dominance. So the charge which will effectively decide the direction will be which charge? Which charge will eventually decide the
The
direction?
first one
The first.
plus Q.
Very good. So the net field at O will be. So if you have discussed the direction already, then only use the value of electric field. Don't write the sign of charge.
But sir, I'm having one doubt
Yes.
here. If both the sides they are having the equal field, then at O it will be 0, right?
But how they are equal? They are at different distance. No?
Correct. Yes.
Because as you go away, then distance will change. No?
Yes. Sure.
So the first charge will. Can I write the value? Okay, I'm writing the value only. Can I write E1 plus E3 plus E5 dot 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 minus E2 plus E4 plus E6 dot dot dot. I'm writing the value and I know this answer is towards left. The net will be left. Why? Because the first charge will have the left direction. So any other charge will have lesser value even if we subtract. So the net field will be towards left. So do you realize this, that the net field will be left? Yes or no?
Yes.
So the E not infinite is what? So because it's just a value we are supposed to write, the electric field formula due to point charge is how much? KQ by R square. Don't write the vector form. Vector form is not required because we know the direction already. So the first charge will create how much field?
KQ by A square.
Then third will be KQ by
KQ by 4A square.
9. 1, 3.
It is 3. 25.
And the odd will have how much value?
KQ by 4A square. 16A square.
Yeah, 16. So I will not write much. So we can take something common. And we are left with 1 minus 1 by 4. But I am just writing in together. I mean 1 by 9, 1 by 16. 5. So now we have this relation. And of course, this is neither GP nor AGP.
Yeah.
So of course, you do not know the answer. So don't worry. So this term is basically called Bessel function, and its value is this much. So you can just remember that this is equal to this value, and this is the answer. Okay.
Yes.
There is one very famous value which you should remember from the expansion or the series expansion in mathematics. So what is the value of 1 minus 1 by 2 plus 1 by 3 plus minus 1 by 4 without the square? Anyone knows this value?
Sir, ln2.
Yeah. Where this is ln2. So it's a basically expansion of ln 1 plus x. And what is the expansion of ln 1 plus x? X minus.
X by 2. Yes.
If I put x equals to 1, what we get ln 2 equals to 1 minus. So in JEE Advanced, such kind of expansion series also asked. This was a very old question of JEE. They asked in 2000 something, or maybe 1996, 97. So you should know the expansion and why they believe that you should be knowing. Of course, you're learning mathematics. So all the series expansion that you see at the end of the any book of mathematics, one should even remember all those expansion. It is also particularly helpful in the solving question of limit and continuity. Okay? Mostly limits question, right?
Yeah, limits the.
Yeah. So the series expansion is a very nice way of understanding the answer. And if x is very small, we can write this equals to this only. All the high power we can ignore.
Yeah.
So that is our approximation also. So ln 1 plus x is roughly equals to x if mod of x is very, very small than 1. So if x itself is very small, we can convert the log into a linear function. And these kind of things are used in solving question of thermal expansion or wherever the approximations are used. Okay, anyway. So just for the idea, we solved this question that why questions like this comes into the picture, you should be aware of.
But the pi square, we wrote the value that is also from some series.
That's called the Basel function. You can read about it in online.
Okay.
So there is a small guy, surname I know, Bothra. So he may be 10 or 11-year-old. He solves all question of JEE Advanced and Olympiad. So he will teach you how to solve Bessel function. You can search and enjoy his lecture. Very small guy teaching the world about mathematics. There are many child prodigies in India which are good with the JEE stuff. So the next question is, okay, now one dimensional question is something that we should not expect much. So the question that you will face is the 2-dimension or 3-dimension. So you will have charges in a plane, not along a line, and then you're supposed to find the net field at a point. In such case, the trick is very simple. I'll show you how. So let me solve one question first. And we have done this in Coulomb's law, so it won't be difficult for you. Let me tell you the way of solving numerical. Okay. So let's say we have an equilateral triangle and charges are on the at the vertex of this triangle. The side length you can choose to be A. That's okay. Let me remove this charge. I don't want. So one of the vertex is empty. So let's call O. You may bring some third charge there, but that's a different story altogether. So our question is, what is the net electric field at O? So what is the net electric field at O? Tell
In
me.
this, we can solve for the Coulomb's law and then put one charge and one.
Yeah.
So we can.
Correct. So the simple way of solving any question of electric field is the empty place or the place at which you are looking for the field, assume plus one charge. And you do the regular Coulomb's law, just find the force. Why? Because in the Coulomb's law formula, if you make one of the charges Q, as 1 coulomb, it will become kq into 1, which is simple, the formula of the electric field strength, right? So if
Yes.
you have the point at which you are trying to find the net field, imagine a plus charge, and the way you used to find the net force, try to find the net electric field. The only difference in the answer will be, in terms of single q, kq by r square term. Okay, so do this. Tell me the answer quickly.
Root
No, it
3
will not
k
take
cube.
how much?
Root 3 k cube.
Yeah. So the solution is root 3 kq by a square, right?
Yes.
So the way of writing will be, just for the sake of writing, the way of writing will be, the bottom charge will create field like this, and the top charge will create field like this. And because they are equidistant and equal strength, so we can say the field will have same value E and E. And again, we can use the concept of angle bisect. So the resultant field is how much? 2e cos 30, which is root 3 into E. E is the field of only one charge. So we have done this before, and I will not repeat much, but just for the sake of writing, we are writing like this. Now imagine if you bring some charge here. Let's say you bring some charge called Q naught. So how much force this charge Q naught will experience?
Root 3 k k k q q naught upon s.
Yeah, so it will be the charge you're bringing there into the field which was existing there before.
Yes.
So we'll come to this formula also very soon. Now we have done all such questions in Coulomb's law. So
Yeah.
for the sake of completeness, we'll be doing just few questions which I want you guys to solve, and then I'll move to the next concept very quickly. So do this quickly. Tell me the answer. If it is a square of side A, and this is the the missing O. So what is the net flat O? Same logic.
K q by a square root 2 plus 1 by.
So KQ by S square into
Root 2 plus 1 by
1 by 2.
2.
Yeah, very good. So these are the values. So we can do similar questions in a similar fashion. So I'll go to the next concept directly, which talks about the relationship between electric field So let's say if I'm not giving you any charge distribution, you are not aware that there is some charge kept somewhere. So you have no idea. And what I'm saying is that at some random location of space point P, there is a field already existing here having value E. So if any charge will come at this location called Q, and the E is the field due to all other charges except Q charge. the Q is coming here to experience it, right? So whenever you try to find the force experienced by any charge, the field will come from the remaining charge except the charge which is going to experience it, because the charge will create a field which will never apply force on yourself. So self force exerting bodies are not possible. So the field of charge will not contribute anything in the force, right? You must have seen that. I mean, if you have a small diya, there is a darkness beneath the diya. Have you seen
Yeah.
this? There is a very famous cliche also. Diya tale andhera.
Yes.
So the diya is representing the charge which cannot enlighten itself. Okay. So philosophically, that's why we seek some guru. What is guru? Who can enlighten you? Because you cannot enlighten yourself. I mean, it's a very difficult process. So we all need some sort of guru. So the electric field is the field due to all charges except this charge. And the relationship is pretty much simple. So we can write the force on a charge Q is Q into E due to all other charges except Q. So what you can say? So having known the field of a location, finding force or force experienced by any charge will be pretty easy to calculate. So we can say in equation 1 or in relation 1, E represents field due to all charges except Q. Okay, so the who wants to experience, their field should not be considered or taken into consideration while calculating. I hope this is very much obvious, right? Why we are
Yes.
doing this. So given E, we can do this. Now, every time you're not supposed to calculate E. Sometimes E is given to us directly. So for example, let's say we'll take a simple example. Let's say this represents the direction of electric field in a space. And you can see the field is everywhere pointing towards right. Okay. So what is representing? The field in space pointing towards right. And who must have created? Can you guess? Who must have created? The answer is pretty simple. It is being created by some charge distribution which is invisible to us. So we should not be bothered about who has created. So some sort of distribution has created, and we are okay with whoever has created it. I mean, it doesn't matter. Now you enter this field, so you are external to the creator, isn't it? Whoever has created it, you're not part of it.
Yes.
Correct. I hope you're getting my point. What I'm saying.
Yes.
So this is the Pandora box. What is this? Pandora box. What is Pandora box? Oh, a mysterious box. Okay, so what we have is we have some sort of a radioactive substance kept here. Oh, this looks like radioactive, no? The green color. The code for the radioactive is green, right? Oh my God. Dangerous. So what we believe that this is packed. And let's make a small hole. So now some rays, alpha, beta, gamma, these rays are coming out of this hole. Okay. So I will show you some path and you have to decode that which particle will be following which path. Okay. So you can see there are 5 paths. Let's name it A, B, C, D, E. So there are 5 particles coming, and I'm believing or assuming that every particle is coming. So few particles, okay, I'm assuming that every particle coming out of this box having same velocity. So velocity is same for every particle. And what are the particles? So we have a collection of particles. So we have to guess the path of each particle. So we have alpha, ray, beta, minus ray. Yeah, beta does not mean only electron, it could be positron also. So we have 2 nomenclature, beta minus and beta plus. So when you say the beta minus, it means you're talking about the electron version of beta rays. We have something more actually. H plus. Of course, gamma will come. H plus ions. Hypothetically, it's coming. So this is Pandora box. It could emit anything. So if I don't have a space, so I'll just choose one more. Gamma. Okay, fine. Gamma. And one more. What is one more? Let's say. Okay, hydride ion. There is something called hydride ion, H minus. Have you heard this name, H minus?
Yes.
H minus is called hydride ion. Yeah? H is unique, very weird element in periodic table. That's why it is having the controversial place. There is no place.
Yes.
And the controversy has got the most privilege of getting the atomic number 1. That's a different story. Right? But place is not decided, right? Anyway, so now coming to this particle, can you just guess the path? Which path? of the
Gamma
particle?
will go from C.
Yeah, so gamma will go
Okay.
for C. That's correct. So I want all you guys to guess. You can guess at least. It doesn't matter whether it's right or wrong. Can you guess? So what about the alpha particle?
D.
Alpha will be B. You're saying B or D? A, B, C, D.
D. Delhi.
Delhi. Okay. I think that's the correct answer. Anyway, we'll see that. So alpha is D. I think D, I think is correct answer. So how you decided that it will be D, not E? What was the basis of your differentiation? Why D, not E?
Alpha has positive 2 charge, so it should be deflected more.
So deflected more means E is deflecting more, no?
So it should have been A also.
But A is opposite. So of course, see, if any charge is positive, will deflect or will experience force towards right.
Yes.
But if any charge is negative, the force will be reversed compared to the field direction. So all negative will go left, that is for sure. All positive will go right, that is for sure. And then C is the path which is not deflecting, which is like it is not getting influenced by the field itself, which is only possible for the neutral particle. I hope this part is clear.
Yes.
Who will get right, who will get left, and who will go straight? That part is clear.
Yeah.
Now, what will be the differentiating factor? How we are going to judge among the other possibilities of the right path? Okay. So, like Kanu said that okay, it's a two charge, which is a good way of thinking. But is it complete? Do you think that this is sufficient to reason the answer, or should we look for something more?
Something that I think.
So, what that would be? If you think that there's something more is there, so what that would be? I mean, you can guess it. So everyone is having the same velocity in the y direction. Let's call the vertical as y. Okay. So deflection is acquiring greater velocity in the x direction, right?
I think the strength will matter.
No, strength is same for all. No? Strength is same for all. So we need some differentiating factor because everyone is going to get the same E. So charge will matter, that is for sure. But I think one point you are missing. Can you guess what is the point you're missing? Anybody please guess something? Okay, so I think I need to intervene. The answer is acceleration in the x direction. We need to check for acceleration, not the force. Force is deceptive. So what really changes the velocity is acceleration, right?
Yes.
A equals to dv by dt. So greater the deviation, which means greater the acceleration, isn't it? Can we say this?
Yeah.
Do you agree, guys? What I'm saying?
Yes.
The acceleration will be the deciding factor, not the force, isn't it? So we need to be careful with the mass also. So let me do this. I think the D is maybe correct. I will check. So let's do the analysis. So whenever it comes to motion, think about kinematics, you'll get the right answer. So what is the acceleration of the alpha particle? So we'll take the basic, the charge is 2e, like twice of the electron charge. And mass I will express in terms of proton. Okay, that's okay. So what is the mass of alpha particle? It's 4 times mass of proton. So it turns out to be okay, charge into E. Force will be how much? Charge into electric field upon mass.
Yes.
I'll like once again. The force is QE upon mass is the acceleration. So acceleration by definition is this only, isn't it?
Yes.
So first of all, we need to know how to write the acceleration, which is pretty easy. Multiply the charge with electric field and divide by its mass. What you get is called acceleration. Is this part clear?
Yes.
So now you can go one by one. What is A alpha? 2e, capital E is same, and mass you can write in terms of proton. So by the way, because E is same for all, the ratio of charge upon mass, what this is called? Anybody knows the name of this ratio? You might have heard before. What this ratio is called, guys? Okay. So from chemistry, I expected you were knowing this. This is called a specific charge. So the charge upon mass ratio, this is a very famous name. JE has used this word many times. Of course, even if you don't know, they write Q by M before they write the specific charge. So generally in question, they define explicitly that what is the specific charge meaning. It is good that you should be aware of this. So charge per unit mass is called a specific charge. And now we can play with the formula. So we can get here E by 2mp. Okay. Similarly, what about the H plus E by only mp? That's done. What about the H minus? Same value. This is the only negative value. So E by mt. Acceleration will be same, but direction will be opposite. So if you want to write in direction wise, you have to put minus sign. That's a way of writing in one dimension. Okay, what about the what is left? Beta minus. Yeah. Here there is a change. The mass of electron will come, ME will come. So now you have the list of acceleration. Can you tell me now what is the right order? So alpha belongs to what? So among alpha and H plus, which one will deflect more?
H.
Correct. So H will deflect more, which means this is the E path.
Okay.
And this is the D path. So, okay, the D path is correct. But deflection wise, H plus is more. So path is E. So what about the path of H minus? So we have two options for negative A and B. A is the maximum deviation. It goes left very early. B goes after some time. So you can see that. So out of these two, which one is bigger? The beta minus, right?
Yes.
Anyone having any doubt in this discussion? What is the path? So the path part is clear. So we can add the alpha will path, choose the path D. H plus will choose the path E, and H minus B, and beta minus A. Oh, one more thing. The gamma C.
C.
Okay, so gamma will not follow the force relation because gamma is a neutral ray. It's an electromagnetic radiation. Actually, it's EM wave. Alpha ray is a stream of alpha particles, so it's not a ray as such, not like light ray. So alpha is called the stream of alpha particles. Beta ray means the stream of beta particles, and so on. Okay, so with this knowledge of electric force, what we can solve in physics? So the moment we know the field in a space or a region, if someone says that E is constant, a uniform field. So for uniform field, can we say that force will be constant for any given charge? So the relation is this, no?
Yes.
When you say uniform, the Q into E becomes constant, isn't it?
Yeah.
So as long as you are part of the field, you will experience the same force.
Yeah.
Correct? And the force will be same not only in magnitude but also in direction, isn't it?
Yes.
So for uniform field, what we can say? Quickly. A charged particle in uniform field will experience constant force in magnitude as well as direction. So I would like to talk about something called path. So what will be the path of the charged particle in uniform field? Can you guess?
Straight line.
So it could be, if released from rest, then a straight path.
Yes.
Because if you are at rest, then the motion will start because of the force itself, and it will take you in the direction of force. But what if you don't start from rest? If I throw you with some velocity, what will happen? Can you guess? So if I impart you some initial velocity, then what will happen?
Path will not be straight line.
Need not to be. It could be, but need
Yes.
not to be. Okay. So now there are two possibilities. There are two possibilities. You may project parallel to the field, or you may not project parallel to the field. So what we can say, guys, if we project parallel to the field, path will still remain straight line. If we project at an angle with respect to electric field, then the path will be
Projected.
exactly parabolic or projectile path. So if you project at an angle with respect to electric field, then the path will be parabolic. And the charged particle will perform the projectile motion. So the entire concept of projectile motion can be brought here, right? So we can again solve the class 11th projectile motion. We'll solve some questions, not all. But I will tell you how to correlate this chapter with the chapter of class 11th. Okay? So the path is very important concept in physics. You need to be very much careful about it. Just so we'll do some one-dimensional question, just one question or two, and we'll go to the two-dimensional. Okay. So imagine we have a rough plane with coefficient of friction mu, and there is a block. The block is having mass m, and it carries charge q. So the charge q is part of the block somewhere, and we apply the horizontal and the uniform electric field E. So unless I'm not saying you have to assume it's uniform. So the first question will be find E minimum required to move the block. Very simple question. You can solve with ease. What will the answer?
Mu mg by
Yeah. So mu mg by
q.
well, that's the right answer. So anyone having doubt in this question? So you must overcome the limiting friction, and limiting friction is how much? Mu into n. Okay.
Yes, which is mu1.
Yeah. And you know how to solve it. The next part will be obvious. So the same question with a slight twist. Now the field is acting at some angle. The angle is even not given. You can choose the angle. Find E minimum. Now I'm asking E minimum. I don't know how it is acting, but E minimum to move the block over the surface. So tell me the answer. This is not difficult.
Hello.
Yes.
E minimum will be mu mg
Mhm.
upon. I took the angle as theta, so q cos theta. Hello.
Yes, yes. Yeah, I'm
Q
listening.
cos theta plus mu sin theta.
Yeah. So Q will be like outside, na?
Ah. Uh,
So the Q into E minimum. We know the result of this from laws of motion. It's mu mg upon.
yes.
This is the answer. This is not minimum. This is the value when you assume theta intimate. And to minimize this, we have to maximize the denominator actually. So denominator will be maximum when we know the answer. What's the maximum value of this? So what's the maximum value of A sin theta and B cos theta?
A square sin square theta.
No. The maximum of this is under root of A square plus B square. Correct? So we have done this in the trigonometry, and I hope that you have done in the mathematics also. So the Q into E minimum will be how much? And that is where the E minimum turns out to be. Is this clear?
Yes, sir.
And what we are doing the again laws of motion. Just the force is replaced by QE everywhere, right? So earlier we used to apply force F in every question, and now we have a privilege of applying the field and doing the same job. Okay. So if you have done the laws of motion, these things are pretty simple. So I'm just repeating the entire physics through this concept, so that you can also revise the old concepts. So we have an inclined plane of inclination theta, and a block is kept over it. Okay. And it is given that tan theta is more than mu. What does it mean? The angle of inclination
Not
is
sliding.
more than the repose angle.
Repose angle.
So it will slide. So if you release it, it will slide, right?
Yes.
Right now there is no field, so it will just go down because charge will have no role to play. So what we do next is now we apply the horizontal field. So a uniform horizontal field is applied everywhere. So even if I draw just one arrow, assume it's everywhere. Don't worry, it's not there. I mean, many students think that okay, if I've drawn here, the field is here. No, field is everywhere. I mean, there is no need to draw everywhere, right? So the question is, There are two questions to solve again from same laws of motion. Find the E minimum to keep the block.
There was a trick also, like from E minimum to E maximum. you have
Stationary.
to replace something from something.
So find the E minimum to, or find the range of E to keep the block stationary. Or the better way will be like find the range of electric field for which the block remains at rest. So again, see what I'm doing is I'm playing with the same laws of motion, the friction question. We have done all questions like this, and that time I was not applying E, I was applying something more. So this is horizontal, which means this angle is theta.
Yes,
So
so we
here,
can do it.
yeah. So try this out and let me know.
Hello.
Yeah, tell me.
E minimum is mg sine theta minus mu mg cos theta upon q mu sine theta plus cos. And maximum will be mg sine theta plus mu cos theta upon
The sign will change, right?
plus mu.
So can anybody else can confirm this just for the sake of confirmation? I think this should be cos minus mu sin, right? Should come here like this.
Yes, you have wrong. Mu will be changed to minus.
Anybody else getting the same answer? Please confirm. Krish, Anu, tell me, guys.
No, sir.
What is your answer then? Are you getting different answer or you are not getting answer?
No, sir. I got similar. Yeah, same answer.
So what we are supposed to write for minimum force, we have to just balance the net downward force equals to net upward force, right?
Yes.
But there is a catch. When the electric field is minimum, the tendency of the block will be to go down, and so the friction will act up. Understood?
Yes.
So I think it's not easy. Let me check the answer. I mean, the normal also gets modified, right?
I break um, QE.
I would taken the normal also into consideration. The electric field also creates the normal reaction.
I will tell what time.
So
First,
first of all,
Mg will break into components.
yeah. So let's say M. Okay, let me just do the same logical way. So Mg cos theta like this,
Yes.
normal like this,
Yeah.
and Mg sin QE sin theta like this.
QE sin theta.
Correct. And the down the plane will be
Mg.
Mg sin theta.
And friction on the opposite.
How much?
Mu n.
Mu
And
n.
also QE component.
And Q. Very good.
QE cost. Yeah.
So now you can balance it to
Yes.
get the E minimum. That's correct. So now you can add mu into Mg cos, also you can add as, let me just rewrite. So mu into n plus QE cos theta so we have okay. So the E minimum turns out to be, so what you got is correct answer. And similarly, you can directly at E max by switching the sign. Yes. So these are some of the laws of motion questions that we have done. Let's do some kinematics. So imagine, well, this, of course, the way of creating is known to us. So let's say we have two plates of a capacitor. You can think as a parallel plate capacitor. So either you have heard before or not, doesn't matter. And parallel plate capacitor can create uniform electric field. So they're known for creating the uniform field. So the arrow is representing the uniform field, which is vertically downward. Think that. Now this is the representing some uniform electric field E. The E is constant. The plate gap is given as, let's call H. The length of the plate you can call is Y. L, you can call it L actually. And a charged particle exactly at the midpoint, you can see, and the charged particle is positive. So we have positive charge particle having charge q and mass small m is projected horizontally like this. And the height is h by 2. And what we like, we can ignore gravity. Generally, electric force is so powerful that gravity will have almost zero contribution compared to the contribution coming from the gravity. I mean, electric force. So if the electric force can create the acceleration of, let's say, 1 million meter per second square, gravity creates only 10 roughly, and therefore it's okay to ignore. In some question, they will tell you to consider also. Now you will ask, "Sir, when I will think that I need to consider." So in JEE Advanced, if a question mentions G value equals to 10, in a question like this, so it means they want you to calculate G also. I mean, take the gravitational effect also. So generally, it will be mentioned in the question that ignore gravity. Many times, from numerical value they give, the calculation will tell you the range of acceleration. So if you calculate QE by M and if turns out to be very large compared to the G, simply ignore it. But if they give QE by M numerical values in such a way that you see that it's quite comparable, maybe you're getting 25 or 30 or maybe 5 itself, then G becomes quite dominant. So from numerical value, you have to do a side test. Should we include or should we exclude if they mention numbers? If they don't mention number, which means we are not supposed to compare, and that is why in most cases we ignore. All right. So when else we need to consider if the options also include G, which means take care of G also. So all these things are contextual. You need to see the context and try to do the best possible guess. So now ignoring gravity, what will be the path of this charged particle? That's pretty easy to guess. So this is the simple case of horizontal potential motion, right?
Yes.
So what are the possible questions? Where it will land, or what is time of
Time of
flight,
flight range.
or what is the maximum or minimum velocity required to exceed the plate or leave the catheter? So what is the minimum velocity of projection? Minimum velocity of projection to leave the catheter, which means it should be thrown like this, right? Maybe slightly more. So just good enough to cross the plate. So question is, oh, let's solve this question. I'm creating it. Find the minimum horizontal velocity of charge particle to leave the plate. It's that simple. So no matter how fast you throw, the time of flight is going to be fixed, isn't it? And in the same time, you have to reach the other end of the plate.
Sure.
Yes.
So to solve this, first I found the
First,
time.
you find the acceleration. Like what is the ax, ay? You can choose the
So
coordinate axis.
AX, okay.
Yeah. So ax will be nothing, zero, right?
Yeah, and AY will be QE by M, right?
Minus q by m, right? It's, if you take
Yes,
y
yes,
up.
down.
So if I choose y as up, the ax is zero, we know. The ay is minus qe by m because we have to find the acceleration, which is force upon mass. Okay. So we got ax, we got ay. What is vx? What is ux? You can say the
It is
initial
V naught.
horizontal velocity v naught.
V naught.
What is uy? G.
0.
And you can choose the origin the way you want, or it's all about, I mean, the choice of the coordinate axis. Can you find the time of flight? So try doing this, the time of flight part. This is very, very common question you will see in every book ever written in electrostatics. Will
Time will
have this
be
question. Yes, time will be. Yeah, tell me.
MH root of
Mhm.
MH upon QE.
Correct. That's the right answer. So the time of flight, we know the formula in right. You can just think of gravitation.
Yes.
Sorry, the normal one.
Kinematics.
The 2h by g, right?
Yes.
So you can think that okay, we have something called G effective, which is QE by M. Okay. So now this is the new G effective, and therefore you can rewrite answer as 2h by G effective in this case. If you also consider the gravity, you have to add G. Okay. So this is like optional, depending on the situation. If you see the option, you can add G also. Right now I'm ignoring it. Okay. So I'll take two cases, ignoring gravity and including gravity. Let's say let's do both. So the H is actually H by 2 and G effective is QE by. So of course the answer is MH upon Q. Very good. So you had this answer. And then
Yes.
to cross the plate, the range must be equal to L. And how we write the range? Ux into time of flight.
It's into
So V naught into T. So the V naught minimum is L by T, which is L into U by MH. I hope this is clear to everyone. Just in case if you
yes.
have not revised the kinematics, do revise. It's the right time to revise. Kinematics is like a golden opportunity to rectify all your mistakes of class 11, because this is such a huge chapter. It contains everything in physics. Everything is everything. You just think about any chapter. I'll give you example. Okay, so this is the V minimum. Okay. You can also find the path of trajectory. So also find the equation of trajectory. Let me tell you the coordinate system. Take the bottom as the origin. Because I want to answer accordingly. Right?
Hello.
Yes. Tell me, tell me. You audible?
Hello. Yes. I'm getting 2y is equal to
How much?
2y is equal to
2y equals to
x square t square
x square.
t square
T square. Okay, T should not come. Na? We only want answer in terms of x and
x
y.
and
Right?
y. Yes.
So if you choose any point P on this trajectory and if you name this as x comma y, so the x coordinate we can attach v not into T
Yes. That.
and the y coordinate we can attach. Okay, so how much you have gone down? So this is the y, height is y.
Yeah.
So can I write like the h by 2 minus y? I'm writing directly. The vertical displacement is half qe by m
QE
into
by
t square.
m. Yes. Correct.
Correct.
Yeah.
And now I can substitute t.
Okay. I didn't expect. I substituted QE by
No, you have to write substitute. You have to replace the common variable, which is time.
Right.
And again, if you want, you can substitute v naught also, because that we have calculated. Okay, so but that's not required. So anyway, this is how you can write the answer. You can write directly the answer how much you are going vertically downward. So h by 2 minus 1 by 2. And this is the question from the NCERT, right?
Yes, it's in the solved example.
Yeah, I think solved. This is in the unsolved actually.
Solved
NC.
also one example is there of project of length.
Yeah. Okay. So anybody else having doubt in this? How to solve? Am I audible, guys?
Yes.
So based on this, okay, I'm not solving many questions of projectile motion because the only idea is you could use the QE by M as a G effective, or you can add or subtract G also, and then solve accordingly. So you have to be very careful that how you uh, create your G effective. Okay. So every question will have a different orientation, and looking at the context, you need to understand what should be the right way to write the G effective. So that part I'm leaving up to you guys because you have enough practice in the chapter of kinematics. Those who are not very much comfortable, I will suggest please do watch the kinematics videos. It's too much. I have put almost 14-15 lectures of kinematics. All are very detailed. So you can watch every topic separately. Let's see some question from the SHM. So if you look from SHM, say we have a simple pendulum. So This same okay. Small q. So we have a pendulum, and you can say the pendulum having mass m and charge q. Okay. Now here I am telling you, okay, don't ignore gravity. Okay. So now what I'll do is I'll apply electric field downward everywhere. Okay. So now uniform field is existing in the downward direction everywhere. And let me show you at least few arrows, but it is everywhere. It's not like it will end somewhere. And we are assuming it to be uniform. So a general formula for the time period of pendulum is what? 2 pi under root L by G. The only difference we will have here is L by G effective. Now here you have to be extra careful. So when the pendulum will oscillate, let's say it is at some random location here. Am I audible, guys?
Yes.
So let's say this bob is at some instant somewhere here. So the bob is here. Now you can draw the ABD. So the force of electric field will be downward and gravity is anyway downward. And tension is like this. So earlier we only used to have the mg, now it is mg plus qe, as you can see. And the restoring force will be at right angle to the thread or the string. So this is the direction of restoring force. So given this angle theta, this is also theta, so you can simply say the net force in this direction is qe plus mg cos theta. And now we know that the F restoring in this case will be.
Sine.
So I'm giving you the derivation, that not just formula, you should know what exactly we are trying to achieve here. And for a small angle, you know what we do further. So what is the acceleration part? The acceleration part, how we write in SHM? The F restoring upon mass, it automatically turns out to be minus QE by M plus G. And the sine theta we can write, okay, you can just take as X and X by L, right? If you remember the for a small angle approximation. And now you can compare with minus omega square x. You know omega square is 1 by L QE by M plus G. So time period will be 2 pi under root 2 pi by omega, which gives you the answer 2 pi under root of L by, I'm writing this entirely below, G plus QE by M. But next time, if you the field is parallel to gravity, you can just add the G effective. That's why we write G effective as G plus QE by M. You can just write directly. So you add acceleration, not the force. We are adding acceleration. So this is a small change. You can also do it just like a formula in which you have to substitute the G effective and get your answer. So if I switch the direction of electric field upward, what will be the new time period?
G minus GE by.
If field is reversed, then G effective will be mod of G minus QE by M. I don't know which one is bigger, right?
Yeah.
And therefore, the time period will change for sure, right?
Yeah.
So they may give you a situation. Let's say the time period of a pendulum is this many seconds under the influence of gravity and the vertical electric field, uniform field. When the field is reversed, then the time period changes to this value. May it becomes 20 second. So find the electric field. So given T1 and T2, can we find the electric field value? So that's a very nice experiment, that by using the time period, we can find the electric field, isn't it?
Yeah.
So How we can solve this question? Just write two equation 2 times and you will get the answer. Okay. So if T1 is this answer, if T2 is given to you, so by the way, T2 is given, is this answer. Let's say the G is still downward, okay, the net force is downward. They will give you that, assume this is less than that. So if both are downward, so we can write like this. So what is the ratio of T1 by T2? And what is the square?
G minus QE by upon.
And I hope you can rearrange the term. So G plus QE by M. Is, we can write as eventually. And this could be a perfect experiment to find the electric field in a space. I mean, that's really nice. So, oh, so we got the answer. QE by M. 1 plus T1 square by T2 square equals to G into 1 minus T1 square by T2 square. It looks really nice. Eh? So E is mg by Q. T2 square minus T1 square upon. Oh, so you can see. So we are able to determine the electric field given the time period. I hope this is clear, guys. Any doubt in this? Okay, so there should not be any doubt. I hope so. So where else we can use this concept? I mean, we are done with the so many things. Of course, we will be doing the work energy power a lot in potential part of this chapter when we discuss the potential energy and potential. So that's why the work energy part I am leaving as of now. So what we can do else is rotational. Let's take some question of rotational in the context of yeah, electric. Rotational balance. Okay. So this is a very challenging problem from some challenging book, which I will not mention to scare you. So imagine we have a uniform electric field in the direction, let's call it right. So now we have the uniform electric field, okay, E. What else we have? So we have a uniformly charged ring. So ring is like this. And this ring is having one small missing part, very small. Okay. This angle is alpha, and alpha tending to 0. Okay. The radiuses are, and the total charge on this ring is Q, except the missing part. A small part I have removed. So what will happen if I release the ring from rest? In the beginning, this part is perpendicular to the E actually. So I might not have done perfectly, but so I am going to release this ring from this state. Mass is M. So the moment I release, what will happen? Can you guess what will happen first of all? So the entire ring will experience force towards right, correct?
Yes.
So center mass will accelerate towards right, because when we have a body, the motion we describe is only for center of mass. And we are believing that center mass is still the center because the alpha is really small. So the center mass will not be affected. So the entire body will go towards right. Is there anything else that can take place here? That will happen?
Ring will rotate.
It will rotate, correct. Why it will rotate? Because the force is like unbalanced. So you can see the missing part will create the unbalance in the rotation, right?
Yes.
So the charge corresponding to the missing part at the bottom, like opposite to the missing section, that charge will be the only charge experiencing or creating the torque about the center mass. So what is the formula of torque? Force into arm length or lever arm.
Yes.
So how much charge we can expect in the alpha part? Can you guess what charge in the alpha part? So we can write in terms of angle. So a charge Q in the alpha will be Q by 2 pi into alpha. Charge per unit angle into alpha angle, correct?
Yes.
So we got the charge. And this charge at the bottom will experience force. Rest charge are balanced, like they have symmetricity. So apart from this charge, the right and left charge are balanced. Okay. So if this is the force, the torque about center mass will be how much?
That force into the ring.
Correct. So torque about center mass will be Q alpha E into R. But the problem is, as it will rotate, the distance from center will change, right? So what will happen due to the rotation? Let me show you. The ring will not be always oriented the way you are looking right now. So what will happen as a result of this rotation? This will turn somewhere here. So let me say it is the gap is now here. Not gap is opposite actually. So gap is somewhere here now. So it has turned somewhere here. And now the force is acting as Q alpha into E at this location. We have to write the answer as a function of theta. Why? Because theta is variable. Okay. So now what is the torque now at this instant when it is something like this? So we are supposed to find the torque in general. So at any instant So the torque about center mass is how much? Tell me, guys. Q into R into what is the arm length from center? How far is the force?
Sin theta.
No, cos theta.
Cos theta.
And now, why we are finding this torque? Because we want to know the rotational work. So what is the rotational work? Torque about center mass into d theta.
Yes.
Okay, not the total work. We are not finding the total work. Only rotational work, because I want to find the omega. In case I need to find the VCM, I can use the the net force, I mean, idea to get the VCM. But anyway, the rotational work is needed because I want to know the omega. Okay. So when it will turn till this position, the torque will become zero at this position, right? The moment the force is here, the torque will be zero, isn't it?
Yes. Yes.
And beyond this, it will try to decelerate, because if you go other side, it will decrease the omega, correct?
Yeah.
So question was when the omega will be maximum. So I can say that till the theta comes 90. So for maximum omega, or for maximum angular velocity, for maximum angular velocity, what we can say, the rotation must go from theta must go from 0 to 90 or pi by 2. So the rotational work done we can calculate from 0 to pi by 2, and this turns out to be how much? Q alpha E R, everything is constant. What is the integration of cos theta? It's a
Sin
sin theta.
theta.
And sin theta from
1.
0 to 90 is 1. And Q alpha is how much? So it's a Q by 2 pi into alpha into E into R. And we know the rotational work always gives the half ICM into omega square.
Yes.
And now we're done. So we could have also written tau equals to I alpha. And yeah, from there also we have got the answer, but that's fine. So we got the work done and we can equate with the half ICM omega square.
Like we can write alpha as
D
omega t omega by d
d.
theta.
Correct. You can get from that to there. I just wrote unnecessary this, but anyway, because I wrote, so I will solve like this. And for ring, the answer is a square. That's simple answer.
Yeah.
So 2 will cancel out. Correct. And R will cancel out. So you got the omega value finally. So the maximum omega will be how much? So this is from the Olympiad. Okay, so you can see that any chapter can be applied using this simple F equals to Q into E. So where else we can use? Of course, we can use in surface tension also, but because that part hasn't come right now. So the moment we come to the electrostatic pressure, I'll show you the application in surface tension as well. So where else we can apply? There are many, like infinite possibilities are there. You can apply anywhere. At least keep in mind that this is just a force. At the end of the day, the moment you write Q into E, you write a force. And because it's a force, it can be used anywhere in physics. Okay, so try to look for the simplicity, not for the variety of problems, because there is no end to the problem. I can keep on solving, you can keep on watching it, but it's good that when you practice, you can realize the application. So I have tried to cover all the aspect that one should be aware of while attempting any numerical. Okay. So the application of electric field and the discrete charge part is done. I may create a variable electric field, and then I may ask you find the work done and so on. So there is no end to it. As I said, one particular question of my interest is this. So let's say we have a pendulum, again same question, of charge q, mass m, and now there is a charge kept here fixed at point of suspension. So can you tell me the time period of this pendulum? Am I audible, guys?
Yes, yes.
So think about it before you answer.
Yes, well, hello. Hello.
Yeah, tell me.
Not in this question, I followed the steps of SHM, but I'm getting something wrong. Actually.
Yes, anybody else who is getting the answer? Krish, Manasvi, are you trying this question?
Yes, sir.
So if you analyze the way we did for the, the first question of a system, you will realize that the charge will have no effect on the restoring force. Do you realize this?
Yes, sir. Yes.
See, if the bob swings to this position, look at this. In SHM, this is very crucial. The mg is acting now this, but the force of repulsion will act like this, the Coulomb force. And therefore, the force which can create the restoring is still mg only, right? Do you realize, guys, what is the restoring force? The restoring force is still the same, mg sin theta, which simply means the presence of charge will not affect the restoring force. So my time period will be same. I hope this makes some sense.
Yeah.
All right. Okay, let me just do one more question that I didn't do that time from pendulum itself. So can you guess if the electric field applied is horizontal? So if we have the horizontal electric field, then what will the time period? Or you can simply say what is the G effective? Either you mention G effective or that. So gravity is down and the electric force is right?
Yeah, so it will not get involved, right?
No, of course, it will have component.
Yes, huh?
Okay. So if you tilt, you can see it will have component. That's not an issue. Here the G effect will be under root of, it's like a vertical, it's a mutually perpendicular force. No? So you have to add both G square plus QE by M whole square. This will dance.
Good.
The rest is okay. You can do it. And again, if you want to analyze it, you have to tilt by theta, then take the component, then check it, you will get dance. So of course, I'm not going to that great detail. That is not required. So we can stop this discussion of electric field. Now we can go to the electric field due to the continuous charge distribution. Let's do some question right now, and some question we'll do in the next lecture. Electric field due to continuous charge distribution. Okay. In case of continuous charge, of course, the first thing comes is we cannot, use the formula. The formula which we are given was due to a single point charge. Okay. So the electric field that we know is kq by r square. And what is the limitation of this formula? You can apply for a single point charge. So definitely the moment I'll give you the line charge, you have to use the principle of superposition. And again, the principle of superposition will have two separate categories of problem. One in which all the r vectors are same, and one in which all the r vector will be distinct. Okay. So we'll solve both the questions one by one. So we'll take the first question. We have done this in one way or the other way in Coulomb's law. Let's do it again. Before we dive deeper, let me explain some few of the distribution of charge. So in physics, we have three types of distribution. Now, charge distribution is something that we create, which can help us in express the terms with some convenience. So we have the first thing is linear charge density. Okay. What is second? Surface charge density. And third is volume charge density. So generally what happens, like the density word, uh, the way you correlate is the mass upon volume. Basically, density can have variety of definition. So volume is the by default understanding. Like when I say density, most of you will think something upon volume. So when I say charge, of course, and we have a symbol for it, so we write a rho. This is called a rho, RHO. This is called sigma, and we have done all this in in the center mass also, and the lambda. So these are three ways to define the distribution of charge. So when charge is distributed over a volume, we define rho, and how we write dq by d volume. In many advanced book, the volume they write as tau for some reason, which no one knows. So charge in a small volume will be density into the elementary volume. Similarly, what about the sigma? So charge per unit area. Some area, you can take a small patch on a curved surface, on a flat surface, no matter what kind of shape is that. And then if you can find the charge is dq, the sigma of that patch is dq by d. And therefore, in case of surface, we prefer writing charges sigma d. And lambda is charge per unit length. The length you can tell it as dl, dx, dy, whatever. And the charge will be lambda into dl. Now again, the distribution of charge may be uniform or may be non-uniform. So for particularly for uniform distribution, if the distribution is uniform either throughout length or area or volume, in such case we can write the total charge by total length, total charge by total area, and total charge by total volume. Only when we have the uniform distribution, this way of writing is okay. While solving problem, the dq relation should be written in terms of various distribution terms mentioned there. Okay. So here we have uniform distribution, needless to say. And what you are supposed to find? The same thing. Can you find the electric field at a point P? And is it a special point? Yeah. So the point P is at a distance from the center of the rod. And how far is this point, guys? R. We have done this question in the Coulomb's law. This is L by 2. This is L by 2.
Yes.
the distribution is uniform, and this is the formula. This is the point formula. So you can cut elementary point charge, you can cut dl length or dx length, whatever, and you can rewrite as k dq by r square, because dq will act as the point charge for which this is the answer. Now here you can see every dq will be in the same line, correct? Because the entire dq is on the same line and the point p is also on the same line, the field will be collinear, isn't it?
Yes.
So here the scalar addition is also okay because direction is not creating any confusion. So do we have multiple direction or a single direction?
Single.
And in which direction, right or left? So the field will be right or left?
Sir, right?
Correct. So the field is right. And if you choose any random elementary part, the field will be right only.
Yes.
So the thing is sorted now. What you need to do next is cut elementary, move x from the point B, cut a dx, a small piece of rod, treat that as a point charge, apply the formula, and then think of superposition theorem. Like just I need to add the value. Okay. Luckily, direction is not the issue, so the addition becomes a simple uh, algebraic addition. Okay. So tell me the answer, guys, quickly.
Hello.
Yes, what is the answer?
AQ upon
Mhm.
R square minus L square by 5.
It's a very famous answer. E equals to. This was your answer, right? Is this your answer?
Yes.
Yeah, that's the right answer. A square. Now, one more thing that we should be aware of, as I said in the beginning, gravitation chapter is no more different from electrostatics. They have similar inverse square law which follows the force criteria. The only difference between these two chapters is the nature of interaction. In electro, as I said, we can have attraction as well as repulsion. Whereas in case of gravity, we have only attraction. I hope this part is clear.
Yes.
So in gravity, we have only attraction, right?
Yes.
So direction will change. But if I ask you a similar question, what is gravitational field strength? Let me write down here. Gravitational So gravitational field strength will have the similar definition. And what is our definition? So strength is always defined in terms of force. And you can write as G as a symbol, or you can write E also. It doesn't matter. We preferably write G only for some reason. You can see the reason very clearly here. We can write G equals to. Don't get confused with the acceleration due to gravity on the Earth's surface. Of course, we use G there also, G here also. So how we write the strength is defined as force per unit mass. Simple. Force per unit mass. So what is the Newton's law of gravitation? Anybody knows? Newton's law of gravitation. If we have two masses,
G M1 M2 upon mass.
so let's say if we have a point mass of value m, and if I want to know the g value at a distance r, so I will put 1 kg mass here. The same logic, we put plus 1 charge. We will find the force first, g m1 m2 by r square, and this will become automatically the gravitational field strength, which is how much?
Same.
Same. Kq by r square is gm by r square. So there's not a much difference, right? And this is exactly the same. So g is due to given mass, I mean any capital mass m. So if you have capital mass or small mass or whatever, so we have written here all this. You can ignore this part.
Here G is the field strength, right?
Yeah, here this
Hmm.
g is the gravitational field strength actually.
Yes.
But by definition, force upon mass is also called acceleration, right? So both will match here, right?
Yes.
So that's like just coincidence, right? That force upon mass is also called acceleration. So gravitational field strength is actually same as the acceleration due to gravity. That's a good fortunate coincidence because of the definition. So this is also called acceleration due to gravity. In electro, we have two different things. Why? Because the force is having different formula QE. So when you find the acceleration, you define QE by M.
Yes.
So Q and M will not cancel, right? It's not like they can cancel. But here we define mg by m, force upon mass. Force will be mg, just like
Yes.
Q,
ML.
but m gets cancelled. That's why the A and G are same in gravitation, but here we have A and G are, of course, acceleration is different from the acceleration due to gravity. So that's like coincidence. In gravitation, you can understand both ways, and both are correct way of understanding. The acceleration due to gravity is actually the gravitational field strength. Okay.
Yeah.
Is this clear?
Yeah.
So if I give you a rod of mass m, length L, and the similar question, if point P is here and the distance is r, so what will be the gravitational field strength? You can say dg is g dm by r square. You can do the derivation.
It will be the same thing, just
Correct. So the answer will be what?
it will be GM upon R. Yes.
So you can see the correlation in definition, and that is why, I mean, we should learn both the things in a similar fashion. 90% of derivation will match. Where it will not match, I'll tell you. And why? So it will not match because we don't have the positive and negative mass concept, right? And therefore, there is nothing like a gravitational or Yeah, gravitational dipole moment. We don't have dipole concept in gravity. Only it is possible in case of charge. So we have dipole in case of charge. We don't have gravitational dipole because of the obvious reason. We don't have opposite charges, opposite masses, right? So
Yeah.
things like polarization will never happen in gravity. Things like, of course, I mean, there is a pseudo polarization ideas discussed in gravitation also, but not physical polarization, because polarization requires opposite polarity of charges, and we don't have the opposite polarity of masses, and that is why the concept like polarization, dipole, and anything related to these two terms won't be existing in gravitation, and that is the only difference between these two chapters. So electrostatic is like a superset of gravitation. So gravitation is a subset of electrostatics, and it's a proper subset. It's not even subset, it's proper subset. Okay, so you just need to keep in these ideas, and as we move forward, we will be deriving more and more. So what I'm doing is, of course, that I will derive in the next lecture, but as a homework, and these are very famous derivations given in every textbook. So I will request you guys to go home. I mean, okay, you're at home. Don't go home. It's like I'm in coaching. I'm saying this word. Go home and practice. So now you can do practice. Try to derive before I derive, of course. So you should try all possible derivation in electrostatics because you are good with integration and elementary. Yes, Chris, you want to say something? Am I audible, guys?
Yes.
So we have a rod, and the D is the perpendicular separation from the rod. Point P is here. The upper end subtends an angle alpha with the what in this line, the perpendicular line. The perpendicular line is the shortest distance between the rod and the point P, and this is beta angle. So given alpha and beta, and the linear charge density lambda is given directly, which is uniform charge distribution. So the question is, find the electric field at point P. Now, before you solve it, we'll discuss something. We will, of course, attempt at home. I will not going to solve at home. Imagine or do some mental, kind of analysis. Like if I cut into small pieces, then every piece will act as a point charge, right?
Yes.
If I cut the rod into small pieces,
Yeah.
so we'll end up creating infinite pieces, right?
Yeah.
And you can see every piece is located differently. Okay. So the distance of every elementary that you can potentially cut from the point P is same or different? The distance between these elementary cut, which will behave as point charge, and the point P will be same or different?
Different, right?
For sure, it's going to be different,
Yes.
isn't it?
Yeah.
The other question is, are they creating electric field in the same direction?
No.
It means every elementary will have a distinct direction,
Yes.
and that is why you cannot use the integration. Why? Integration is a numerical calculation, and integration can only add numbers, not the direction. Okay. So the problem is you cannot integrate. So what you can do? So the rule is you can take component and integrate each component separately. Why? Because components are like numbers, isn't it?
Yes.
So the way to go is you choose one element to find the electric field at the point P, resolve into X and Y. And once you have resolved into X and Y, you can do the integration with every component separately. And that is the trick of solving this question. Okay. So given this hint, you can try, you can read any book. These derivations are given everywhere. So I will suggest that you can start from SC Verma, check the derivation. First you try on your own, think, I mean, at least play for 1 hour, minimum 1 hour. If today you will spend 1 to 3 hours only deriving this formula, let me tell you, you're going to be the boss of this chapter, electrostatics. And not only electrostatics, if you really practice this, you will feel a lot more comfortable in the chapter coming, like capacitor, current, electricity, and magnetism. Because going forward, all such derivation will always repeat itself in one form or the other. So from here onwards, what we are going to see is some sort of repetition. So once you put your hard work, flesh and soul in this question or questions like this, the journey ahead will be quite smoother. So choice is yours. Either relax, don't do anything, wait for my turn, or the other way around. Okay. So with this, I will stop today's lecture and we'll see the derivation of variety of things in the next lecture.
Sir, on Tuesday, 1 hour early for the rotational doubts.
Pardon?
Tuesday, rotational doubts.
Right. So on Tuesday, let's keep from 5 o'clock.
5:30 will be fine for me.
Okay, 5:30. So let's keep it 5. So
Okay.
it's your duty to remind me. Okay.
Yes, yes.
All right.
Okay.
So all right, guys. Take care. Bye bye. Good night.